Here we go. Okay, so we were finding the generic antiderivatives, but we can also find specific antiderivatives if we're told more information to actually figure out what C is. So say I wanted to find the following antiderivatives using the given value of f of 0. So remember, the capital F is kind of notation to, kind of denote the antiderivative. So when we see these capital letters, we'll think antiderivatives. Okay, hopefully that worked. So we want to find, actually, let me do this before we get started. So notice in this statement, it says the antiderivative. If you see the antiderivative, it's going to mean that you're going to know the C value. Or shall I say, you'll be able to find it. A lot of times, if they want us to find the thing we were doing before, where we just have the generic plus C at the end, they'll usually say something like find an antiderivative or find the most general antiderivative. I do want to say on your Wiley homework, most of the time it'll accept it if you don't put the plus C. And the reason for that is if you just let C be 0, then technically the answer you put in is correct. But be very careful. It also accepts it if you put the plus C. So I would suggest, if you haven't done it already, but if you've done it, it's perfectly fine. Putting the plus C in your Wiley just to get used to it, because the questions that I ask you, I always expect the plus C at the end. So Wiley, their very specific phrasing, will accept it without the plus C. But the plus C is kind of the better answer, if you will. But anyway, so there's kind of a difference here. We have the most general antiderivatives and then a very specific antiderivative. So if we want to find the, so note that the coding language that I use to write these puts the dx very close to the function that it's next to. So don't think that that's just one whole thing. It's 2x dx. So once you see the d, it kind of separates it into a separate piece. But anyway, so the first thing is we actually need to take the general antiderivative of 2x. So we're essentially starting with 2x to the first. So we want to use our anti-power rule. Now that 2 in the front kind of comes along for the ride, unless you see what's going to happen with it. We're going to add 1 to the power and divide by the new power. And we do need our plus C for right now. We're going to figure out what that value actually is. Of course, those 2's can cancel each other out. We'll just get x squared plus C. So now essentially the thing that's different with these ones is they give us information to tell us essentially when we plug in 0 to the antiderivative, we should get 6. So essentially if we let x be 0, we should get 6. Which leads to C being 6, which is a coincidence. And I'll talk more about that in a second. So essentially the antiderivative that we want here is x squared plus 6 specifically. So we did the same thing we were doing the other day where we found the general antiderivative with plus C, but now we're taking this extra bit of information, plugging it in to be able to find the C value that we want. Oh, sorry, Sam. I'm just seeing that right now. Yes, hold on one second. Where's my little thing that lets me? There it is. There we go. So we found the general antiderivative, used that f of 0 equals 6 to plug in 0 and set it equal to 6 to find our C value. So if we do the next one, so let me try to scroll down a little bit. I'll try to keep, there we go. I can keep most of that in there. So here, again, we want to take the general antiderivative first, so the one with the plus C, and then use this information of when we plug in 0, we get 10 to solve for C. So if we want the most general antiderivative, that 6 comes along for the ride. And then we need the antiderivative of x squared, so that's kind of our anti-power rule. So we add 1 to the power and divide by the new power. And then we have to subtract the antiderivative of 2, which is 2x, and then plus C is our antiderivative. We can, of course, take that 6 divided by 3 and reduce it to 2. And now we're told if we plug in, whoops, we plug in 0, we will get 10. So if we plug in 0 here, those first two terms reduce to 0. We end up with c equals 10. So we get the antiderivative we want is 2x cubed minus 2x plus 10. Now, I want to stress here that in both of these cases, the number we were given as the extra bit of information turned out to be c. That does not always happen. So one thing that could happen is, notice in this case we were both given f of 0. We might not be given f of 0, we might be given f of some other number, which we'll do a couple of those in a second. But also, I also don't want you to think that if, okay, well then if it's f of 0, it gives me c. Not necessarily that case either. Okay, so since these both turned out to be polynomials, it kind of turned out to be the case, because if you plug in 0 to a polynomial, you just get the constant at the back. But be very careful. Don't assume that that extra piece of information is just automatically your c value. Sometimes it coincidentally turns out to be the c value, but there are times that it doesn't, so you do want to plug it in fully and solve for c. Questions on that before we move on to the next ones? I'll wait a couple of seconds in case someone's typing. Okay. So let's do 2 more of these. But instead of giving f of 0, we're going to be given some f of some not 0. So here we have the integral from 1 over x plus 1, and we're given that the antiderivative when we evaluate it at e should be 2e plus 1. I know that looks like it's going to be super gross, but it turns out to be a little nicer than you think it is. So here we need the antiderivative of 1 over x. So remember that this is technically x to the negative first, which is the only one that doesn't use the anti-power rule. So this is the one where we have the natural log of the absolute value of x. We went over last time why there's that absolute value. So remember that it's essentially because you can take the derivative of natural log and natural log of negative x and get 1 over x. So we need that absolute value there. Plus the antiderivative of 1, which is x, plus c. So this is our general antiderivative. And then we're told if we plug in e, so let's plug in e, that should equal 2e plus 1. The natural log of e, you might remember this off the top of your head, or you can just punch that into a calculator. That's 1. So essentially, if we subtract that e from both sides and subtract the 1 from both sides, we get that c equals e. So the general the exact specific antiderivative we're looking for here is the natural log of the absolute value of x plus x plus e. So here, again, like I said before, that value, extra value that we were given didn't give us c. We had to actually solve for it this time. And in a little bit more algebraic terms than the last two. Okay. This last one has a couple fractions in it. Don't freak out. All right. But so we need the general antiderivative first. So that 3 comes along for the ride. This is technically x to the first. So if we do our anti-power rule, add 1 to the power, divide by the new power. So x squared divided by 2. The 2 comes along for the ride in the second piece. Add 1 to the power, we'll get x cubed divided by 3. Because we have to divide by the new power, plus c That's our general antiderivative. And then we're told if we plug in 1, this should equal 3. And we'll be able to solve for the c value. So, well, let me rewrite this really quick. So I'm going to write it as 3 halves x squared plus 2/3 x cubed plus c. And then I'm told if I plug in 1 for x, I should get 3. So we got to do a little bit of algebra here. Let's go ahead and just do it in our brains instead of our, well, I'm going to do it in my brain instead of the calculator, but you could always pull out a calculator if you needed one. Now I want to combine together these two fractions, so I'll need a common denominator. I've got a common denominator of 6. So then I have to multiply the first fraction by 3, so I'll get 9/6, and the second fraction by 2, so I'll get 4/6. So I'll get 13/6 plus c equals 3. And if I put that 3 over 6, 6 times 3 is 18, so that'll give me 18/6. And I ran out of space. So then we'll have that c is equal to 18/6 minus 13/6. So 5/6. So the general antiderivative we want here is 3 halves x squared plus 2/3 x cubed plus 5/6. So that one had a couple fractions in it, but not too bad. You just take your time with it. What up, Kayla? Or maybe you're typing, so I'll just hold on a second.
How'd you get the 9/6?
So I have 3 halves, and I want to change it into something over 6. So to get from 2 to 6, I have to multiply by 3. Now my space is stupid. And so that means that I'd have to multiply the numerator by 3 as well. Kind of similar with getting from 2/3 to 4/6. To get to the denominator of 6, I had to multiply by 2. So I have to multiply the numerator by 2 as well. So just common denominators with fractions, but might be a little rusty on that, which is fine. Most of the time people rely on their calculators for fractions, myself included. Any more questions about that one? Okay, I'm gonna erase the thing I just wrote down so people don't get confused when they look at it later. So that's pretty much 6.2. So now we've got to talk about 6.3, which is very similar. So from the fundamental theorem of calculus, which let me remind ourselves what that is, it's at the top of these notes. Yeah, that would definitely change things. So the fundamental theorem of calculus we wrote down at the very beginning of these notes, but I know that that was the other day, so let me remind us what the fundamental theorem of calculus says. It says this. So now essentially what we're doing is we're going away from the integrals without bounds, and we have to talk about the integrals with bounds. So we can essentially use this fundamental theorem of calculus to calculate these integrals by hand. Now I know I already told you how to put them in your calculator, but you need to know how to do them by hand also. So what we're going to do here is the first thing we actually need to find is essentially do what we were just doing. We're going to find the general antiderivative first. But then essentially it tells us that if we plug in our bounds at the end to that general antiderivative and subtract the two, that will get the answer that we want. So, well, let me do this first really quick. So if we look at this first one, if I put that in my calculator, this gives me 8. So let's see if this process by hand also gives us 8. The one screen is lagging a lot. There it is. So essentially what we need to do is we need to find the general antiderivative, and then we need to plug in our bounds. So we need to find the general antiderivative of 2x. So the 2 comes along for the ride. It's technically x to the first, so we'll add 1 to the power, divide by the new power, plus c, which reduces to x squared plus c. Now with these, because we have these bounds, what I like to do is I like to remind myself that I'm not done yet by kind of putting those bounds at the back. And that's pretty common notation, is to find the general antiderivative and then change those bounds from on the integral to just like a bracket on the end. Sometimes people will just use a straight line. I personally like the bracket notation better, but whatever floats your boat. So essentially you do the thing we were just doing. You find the general antiderivative, but now what we're going to do is we're going to plug in those bounds to that antiderivative. So the first thing we have to do is we have to plug in the top bound because it's f of b minus f of a in our fundamental theorem of calculus. So we're going to take 3 and we're going to plug it into this function in x. And then we're going to subtract what we get when we plug in 1. Now we don't need to know what c is here because essentially every single time we do one of these, since we would have to distribute this negative, the c's actually cancel each other out all the time. So what you're going to get is you're just going to result in a number. So we'll get 9 minus 1 is 8, which is exactly what we thought it should be. Now, for your 6.4, 6.3 homework, there's going to be a lot of these that say find the exact value or something like that. The word will be in there. So, note that, well, yes, I understand that you can put this in your calculator. If the answer would be something that was a fraction, something that would include e's. So if we get to the very last example in this piece, we'll see one. So you will need to leave it as like 14 over 5 or 2e to the 7th minus 1. So like if you punch it into your calculator, it's not going to give you this, and it might not even give you this. So homework questions that are going to force you to do it by hand, even if you're trying to just use your calculator, because you do need to know to kind of do them by hand. So just be aware of that and do them by hand. Scroll. Scroll. So just like with the regular derivatives, I'm just going to kind of keep on a roll and just stop me when you need to stop me. So if we look at this next one, we want the integral from 0 to 2 of 6x squared. So the first thing we need is the general antiderivative. So the 6 comes along for the ride. We have x squared, so we have to add 1 to the power and divide by the new power. So x cubed over 3 plus c. So 2x cubed plus c. And we need to go from 0 to 2. So we take that top bound of 2, plug it into the function. And then we subtract off what we get when we plug in 0. Again, those c's are going to cancel each other out because we would have to distribute that negative. So we essentially have 2 to the 4th, which is, I didn't write down, I'm pretty sure that's 64. 2 to the 4th is 16, sorry. Minus, oh yeah, I should have known that. And then 2 times 0 cubed is going to be 0, so our answer here will be 16. So it's kind of like we're doing what we were doing on Friday, where we're finding general antiderivatives, but now we're just taking one step further and plugging in some numbers. Okay, so I actually want you guys to try number 3 first. So that's the integral from 0 to 2 of t cubed dt. I feel like the t doesn't quite look like a t. So I'm going to give you 2 minutes to try that before we talk about it. I will sit here in awkward silence. If you get done that one, you can try number 4 too. I'll give you another minute. All right, so your most general antiderivative should be 1/4 t to the 4th plus c. Added 1 to the power divided by 1 divided by the new power. And then we have to plug in 2, so we'll get 1/4 times 2 to the 4th plus c minus what we plug in what we get when we plug in 0. C's will cancel each other out. 2 to the 4th, that's 64, right? No, that was the same as last time. 2 to the 4th is 16. So 16 divided by 4 is 4 minus 0, so you'll get 4. For those of you who didn't have time to try 4, I'll give you 30 seconds to try to start it once the screen. There we go. 30 seconds to try to start that one. Okay, so your most general antiderivative should be 4x squared plus 5x plus c, and we have to go from 1 to 2. So then we plug in 2 and subtract what we get when we plug in 1. So we've got 4 times 2 squared plus 5 times 2 plus c minus 4 times 1 squared plus 5 times 1 plus c. 2 squared is 4 times 4 is 16 plus 10 minus 4 minus 5. Make sure to distribute the negative whenever you have multiple terms in that last piece. So we essentially have, what is it, 26 minus 9, so 17. Questions on those before we go on to the next one? Okay. These last three are kind of, well, not quite number 6, but the 5 and 7 are kind of what I mean by be careful with the Wiley homework and the exact answers. Because these ones are a bit different. Like if you were to punch 1 through 4 into your calculator, you would just get the number 8, 16, 4, and 17. So Wiley wouldn't really know if you punched it into your calculator or not. But on these ones, the answers are somewhat a bit more specific. So anyway, on this number 5, the first thing we should do is rewrite this as negative 4x to the negative third, because remember, just because you have something, an x thing doesn't mean it's the natural log case. It's only when it's a first power in the denominator that it's the natural log case. So here, this is technically an anti-power rule. Negative 4 comes along for the ride. Add 1 to the power, negative 3 plus 1 is negative 2. The new power plus c. So we'll get 2x to the negative second plus c from negative 4 to negative 1. One screen's lagging. There we go. So we plug in the top bound first. It's always the top bound minus the bottom bound. So we have 2 times negative 1 to the negative second plus c minus 2 times negative 4 to the negative second plus c. Because we're trying to go for the exact answer here, I would suggest changing these over to the fractions again and trying to do it more in your head than in your calculator. Or you can do it in your calculator. You just need to be slightly careful that it's not giving you a fraction, or if it is, that you're changing it back. So this is essentially what we'll get once those c's cancel each other out. So we'll get 2 over 1 minus 2 over 16. Which is essentially 2 minus 1/8. Which if we think about 2 in terms of pieces of 8, we'll get 16 over 8 minus 1 over 8. So 15 over 8 would be our answer for this one. Questions, concerns about that one before we move on? Or as always, tell me if I'm going too fast or anything like that. Even after almost a whole semester of it, I'm not used to teaching at a screen. Okay. So this next one, let me try to leave it in like, oh. Yeah, Kayla, so without bringing it out of the fraction, I don't know how to take its antiderivative because that's not a natural log situation because it's not x to the first in the denominator. I don't have like anti-quotient rule or anything like that. So I need to make it into, you know, the only antiderivative rules we have are, ooh, that screen's lagging a lot. Come on, you can do it, screen. Go, screen. So the only antiderivative rules we have are these. So we need to make it look like one of these. So it doesn't look like 1 over x by itself, so it can't be that one. It doesn't have an e in it, so it can't be that one. It's not just a constant, so it can't be that one. So I have to be able to put it into some kind of x to the n situation. So that's why I to a negative exponent, is because otherwise I don't know how to take its antiderivative. So whenever you have a fraction with the x in the denominator, If it's more than just a power of 1, you need to change it to the negative exponent, because then it turns into a negative, anti-power rule. If it's just x to the first in the denominator, then you're in the natural log case. But if it's x to the any power besides 1 in the denominator, you need to switch it. So hopefully that made sense. Which is why in this next one, integral from 1 to e of 1 over x, we don't have to change it because it's x to the first. So since it's x to the first in the denominator, it's the natural log situation. We have that the antiderivative is the natural log of the absolute value of x plus c. And we're going from 1 to e. So we plug in e, plug in 1, whoops, absolute values. The c's will cancel each other out. We'll essentially get natural log of e minus natural log of 1. Natural log of e is 1. Natural log of 1 is 0. So we just get 1. Now, I do want to say something about this one before we move on. Say that wasn't an e, it was a 3. So we had natural log of 3 minus natural log of 1. You would need to leave the natural log of 3 as the natural log of 3 in Wiley. The only thing you can do is say you have the natural log, so side note really quick, side note of the natural log of the absolute value of 3. You can just write that as the natural log of regular 3 because the absolute value of 3 is just 3. But in Wiley, if you have a question where you're finding one of these for a 1 over x situation and it doesn't just reduce like this one did, you'll need to leave it in terms of natural logs for Wiley or else it'll count it incorrect. Any more questions about that one? I'll wait a couple seconds before we do this last one. Okay. So in this last one, we're in essentially an e to the something situation for our antiderivative rules. So the 8's going to come along for the ride. And then remember, when we have an e to the kt, we still have that e to the kt, but we divide by that k value now, or bring it out as a fraction of 1 over k, however you like to think about it. Plus c, so we'll get 4 e to the 2t plus c from 0 to 1. Plug in the top bound. Subtract what you get when you plug in the bottom bound. And this is, again, where you need to be really careful because we have 4e squared minus 4e to the 0th power. 0th power. Remember, anything to the 0th power is 1. So this is kind of what Wiley would be expecting. 4e squared minus 4. If you put that into your calculator and got a decimal, it wouldn't accept it. So be really careful on the 6.3 Wiley homework when it says find the exact answer. They are looking for exact answers. That is the last question in 6.3, because that's pretty much exactly what 6.3 is on. It's just, these are called definite integrals. I don't know if I've said that yet. These are called definite integrals. Let me kind of write that as a side note down here. So the integrals without bounds, these are called indefinite integrals. I know I've said that because we actually had the definition, but I don't think I formally defined the definite integral as this. So this is a definite integral. In case you hear me saying that word. And so essentially 6.2 was about indefinite integrals, and then 6.3 is about definite integrals. So are there any questions about those before we lightly start 5.3? We're not going to get too far, but we'll start. I'll wait a couple seconds in case someone's typing something. Oh, and I have to get up 5-3 notes. We'll do that while I wait. Okay, I'm not seeing anything, so we will switch over to 5.3. So I forget if I mentioned this or not, but we're kind of going to jump around a little bit. Where is it? Why are you not letting me? Let me show these ones, please. Let me share it. Okay, fine. I'll do this then. So, sorry, again, I don't know if I remember mentioning or not. We're kind of jumping around a little bit. So we were in chapter 5, and then we were in chapter 6. Now we're back to chapter 5, and eventually we'll be back to chapter 6. But yeah. So we're going to talk about this a little bit. So section 5.3 is about the definite integral as area. So from 5.1 and 5.2, the Riemann sum stuff, we do kind of already know that the area, and I kind of was babbling about this earlier, the area under the graph of f, whatever function we're working over, between a and b is exactly equal to the definite integral from a to b of f of x dx. So again, really important to remember that those two are actually linked. So say I wanted to calculate the following two integrals. So let's go ahead and do those by hand. I know we could punch those into our calculator, but since we were just doing it by hand, let's do these two extra ones by hand. Now, in terms of, well, I'll get there when we get there. Anyway, so if we're doing this by hand, we need the antiderivative, so we'll need x cubed over 3. So I'm going to run out of space if I do too many lines, so I'm just going to simplify that to 1/3 in the front, minus x plus c from 1 to 2. So add 1 to the power, divide by the new power. I just brought the division out as fraction in the front. Plug in the top bound. Subtract what you get when you plug in the bottom bound. We'll get 1/3 times 8 minus 2 minus 1/3 plus 1. So essentially, if we focus on combining, like if we're trying to do this in our head a little bit, if I combine together essentially the 8/3 and I subtract this 1/3, I'm going to get 7/3, and then the -2 plus 1 will give me -1, which is 3/3. So we'll get 4/3. That one, it's not as bad if you do it into your calculator, but I wanted to do it by hand since that's what we were just practicing. Now, what if we do the exact same integrand? So remember, the integrand is the function that we're working with. So still x squared minus 1, but now instead of 1 to 2, we're going from -1 to 1. So we're still using that same antiderivative, so I don't really need to think about finding that again. But now we're plugging in 1 and -1. Yeah. That works, yeah. Cool. And then we plug in -1. And I'll just save us the algebra and the time and just tell us that this is -4/3. If you found these as fractions, it wouldn't be the end of the world. Remember, it's mainly Wiley's thing that you need to do it exactly to 4. So if you even just punched this into your calculator and found negative 1.3 repeating, that would be fine. But so if these integrals are supposed to be area, one of them turned out to be negative. And, you know, we usually don't say we have negative area, so what happened? So let me try to keep a little bit of that in there and zoom out maybe a little bit. There we go. So let's try to consider that in terms of these integrals on the graph, x squared minus 1. So if we think about the first integral we were doing, so the first integral, the 1 to 2, well, that would be from here to here. So that would be essentially this area that I'm shading right now. Ooh, let me shade it in actually a bunch. There we go. So it's that area right there. And then the second integral we found from negative 1 to 1 would be this area in here. So if we're looking at one of these areas and one of the areas is positive and the other area is negative, well, what's the only kind of difference between the two? And in this case, the first area ends up above the x-axis and the second area ends up below the x-axis. And that's actually exactly what's going to get us these kind of different signed area. So essentially what happens is when the function is positive for some x values and negative for others, say we have a is less than b to just make the balance make sense. Ooh, I did a bad. I didn't put a dx on here. Ooh. So the integral from a to b of f of x dx is going to be the sum of the areas between a and b. And we're going to have the areas above the x-axis. Those are going to be counted positively. And the areas between A and B below the x-axis are going to be counted negatively. So essentially any area that ends up above the x-axis is going to be treated as positive, and any area below the x-axis is going to be treated as negative. So I'll hold on for a second in case y'all are catching up to that. Now, before we get too much further, I do want to clarify that if you're asked to do these integrals in general, you just calculate the integral like we were just doing in 6.3. What we're going to find in 5.3, which we might not get to until Wednesday, is that sometimes we want to consider it, and we kind of need to consider the fact that some of it's counted as negative. So we're going to need to break it up. So we'll see that in a second. Any questions? Okay. So say we have a function x cubed and we want to find the integral from -1 to 1. So let's just do that. Now, again, when we're asked to just calculate the integral, we just do what we did in 6.3. We just find the antiderivative, plug in the bounds. So if we find the antiderivative, we have x to the 4th, and then we're going to divide by 4, so I'm going to bring it out as a fraction in the front. And we're going from -1 to 1. So if we plug in our bounds, we plug in 1, and then we subtract what we get when we plug in -1. So the c's will end up canceling each other out. We're essentially going to get 1/4 minus 1/4, which is 0. So again, if you're thinking about this in terms of area, that might not make a lot of sense. But essentially what's happening is if we look at the graph of x cubed, it looks like this. So essentially the area we're finding here is we essentially have area underneath of the x-axis to the left. And then we have area above the x-axis to the right. And essentially what's happening is essentially they're the same amount of area and they're canceling each other out. But there's stuff there. Like there's obviously area underneath of that function. It's just that since some of it's treated negatively, it cancels each other out. But what if I actually asked you to find the total amount of stuff that I just shaded in there? Like I want to know how much stuff that is. And that's kind of the difference between calculating a general integral and finding what we're going to call total area. So I don't know if we'll have time for an official example, but let's write down the process. So here's what's gonna happen, and I'm kind of collecting two processes into one here. So we're not only going to be looking to answer questions like I kind of just posed, like here's x cubed from -1 to 1, how much stuff is there? We're also going to want to be finding area between two functions. Now the process can be viewed kind of as the same thing. There's a slight difference. You can find the total area in a little bit of a faster way, but we're going to do it all at once because I find that when I separate them into two separate processes, people get too confused. So, but if you know calculus already and you kind of know the other way to do it, feel free to do so. But anyway, area between two functions and total area. So kind of two processes at once. What you're going to do is you're going to find where the two functions intersect. So the first thing you essentially need to do is find the two functions you're looking over, and you're going to set them equal to each other. So you're going to find where they intersect. So you're going to essentially take the two functions you're working with and set them equal to each other. So in a question like I was just posing of how much stuff is there underneath of x cubed, essentially with those types of questions, your g of x, your second function that you're using, is 0. It's essentially using the x-axis. So sometimes you're given a separate function and sometimes you're just asked about the x-axis. So remember that the x-axis is technically y equals 0. And again, I don't think we'll get to an official example. Actually, we're almost out of time. Let me just write this down really quick. So for total area questions, as I kind of just said, use y equals 0 as your second function. We're going to have to then split up the integral because essentially what we need to do is we need to treat the stuff that's below the x-axis as positive. So we kind of need to split it up where it crosses the x-axis. And sometimes we're also, you know what? I'm going to explain this later on Wednesday because we're actually out of time. And if I keep running, it's not going to be good. So I'm going to go back over this on Wednesday. But that's essentially what we're building up to, is that we have this idea of area underneath of functions, underneath of the x-axis being negative. So we're going to want to essentially treat it as positive to find out how much stuff there is. But we'll talk about that more on Wednesday. What is your quiz going to be on Wednesday? Your quiz on Wednesday will be on 6.2 and 6.3. So antiderivatives and finding both definite and indefinite integrals. Integral. I think I spelled that right. So essentially the thing we were doing right before we switched over to 5.3. So either finding a antiderivative, I could also ask you to find an antiderivative where you have to solve for c, and then also calculating these definite integrals. And yes, you will have to do them by hand. Yes, I will expect you to show me your work. So you can't just plug it into your calculator. You can plug it into your calculator to check your answer, but I will need to see your work and your antiderivative that you found and the things that you plugged in and all that jazz. Anyway, we're out of time. So have a great day. See you on Wednesday. If you have some questions, feel free to stick around for a little bit.